So in this lesson, I'm going to be talking about another type of equilibria, which is your solubility equilibria. The solubility product constant is KSP, and so we're going to be using the same techniques that we used in the last couple of videos, but now it's with a new concept, which is studying how soluble a solid is in water. Okay? Now there are two terms that we're going to be using, and I want to make sure that we're clear on their meanings. The first is molar solubility, and then KSP. Your molar solubility is the amount of solid that dissolves, and so that's going to be your X. So in previous equilibrium problems where we subtracted by X or added by X, here we call that the molar solubility because that tells you how much of the solid is going to dissolve. Your KSP, your solubility constant, is the equilibrium constant for the equilibrium between your ionic solid and your saturated solution. So that's just your equilibrium constant, while molar solubility is the change in concentration or the change in the amount of solid you have. So the first thing that we need to be able to do is actually write out the equations for the dissociation of an ionic solid. So if I'm given calcium fluoride, it's going to dissociate into its ions. So its ions are going to be calcium ions and 2 fluoride ions. So that's the dissociation of calcium fluoride. What I now can do is calculate the solubility constant for a process like that. So KSP here is going to be equal to, well, the concentration of calcium ions times the concentration of fluoride ions squared, remember products over reactants, and then I might be tempted to put that over calcium, the concentration of calcium fluoride, but keep in mind because this is an ionic compound, it's a solid, and so we're not going to include the solid there, and so for your solubility constant expressions, you only include your products because your reactants, by definition, are going to be solid, so we're going to ignore them. So let's look at an example. So here it first asks me to write a balanced equation for calcium hydroxide dissolving in water. So I start off with calcium hydroxide, and it's going to dissociate into its 2 ions. It's going to dissociate into calcium ions and 2 hydroxide ions. There you go. So now, if I look at the next question, it says the solubility of calcium hydroxide is 0.012. Keep in mind that the molar solubility simply means your X. So the concentration of calcium ions and hydroxide ions is going to change. The X for this is going to be 0.012. So I'm actually going to rewrite my dissociation right there. I'm going to create an ice chart because this is an equilibrium problem. Keep in mind, because calcium hydroxide is a solid, I'm going to ignore that completely and just look at calcium and hydroxide ions. So I don't start off with any calcium or hydroxide. I know that I need to add X and add 2X for the hydroxide. However, keep in mind, I've already been told what my X is. My X is 0.012. And so what I can do is say, all right, at equilibrium, my concentration of calcium ions is 0.012, while my concentration of hydroxide ions is 0.012 times 2, which gives me 0.024. So those are my 2 answers for right there. Really not that bad. The last thing I need to do is to write the equilibrium constant expression and calculate my KSP. Well, again, KSP equals simply my products, so calcium ions times hydroxide ions squared, over my reactants, but again, remember, because it's a solid, I ignore it. So all I have to do now is plug in the values I got for the equilibrium concentrations of calcium and hydroxide ions, and I'll get my equilibrium constant, just like what we were doing before in the previous lessons. So I'm going to take 0.012, multiply that by 0.024. Remember, I need to square that value because there's a coefficient of 2 for hydroxide. And what I end up getting for my KSP is 6.9 times 10 to the negative 6, and that's it. So in the previous problem, I asked you to take the molar solubilities and to calculate your KSP. And in this problem, I'm giving you your KSP and asking you to calculate your molar solubility. So it's going to be the same steps, but here I'm solving for X now instead of solving for KSP. So here I'm going to write out my dissociation reaction. I've got copper carbonate breaking apart into copper ions and carbonate ions. I create my ice chart. Remember, I'm going to put an X for copper carbonate because it's a solid.
My initial concentration of copper ions and carbonate ions is 0 for both of them. Then my change is going to be plus x and plus x because there are no coefficients. And so at equilibrium, it's just going to be x and x. So I know my KSP, so my KSP expression is going to be the concentration of copper ions times the concentration of carbonate ions, and that's it. Which means it's just going to be x squared equals my KSP, which is 2.5 times 10 to the negative 10th. So to determine the molar solubility, all you have to do is take the square root of 2.5 times 10 to the negative 10th, and you get 1.6 times 10 to the negative 5th molar. And so that is your molar solubility.
What we're going to look at in this section, there are 3 different factors that can affect the solubility of an ionic compound, basically its ability to dissociate into its ions. And the first one is one we've actually already looked at, the common ion effect. And so just as a review, the common ion effect tells us that the solubility of a slightly soluble salt is going to decrease if there is a second solute present that has a common ion. And so we actually already looked at this in this unit, but let's look at an example to make sure we're clear. So if I give you lead 2 chloride dissociating into its 2 ions, lead ion and the chloride ions, if I were to add HCl to the system, what's actually being added that I care about is that chloride ion, because notice I have chloride in my products for this. And so chloride's being added, and so that's going to cause a shift, and remember this goes back to the previous unit with equilibrium, it's going to cause a shift to the left because I've increased my concentration of chloride ions. So the shift is going to be to the left, and so if you think about the solubility of PbCl2, if you've shifted to the left, that means lead chloride is going to be less soluble, so the solubility is going to decrease. If it had shifted to the right, then the solubility would have increased. So that's one factor that affects solubility. The second factor is pH. Okay? So if we look at, for example, magnesium hydroxide dissociating into its ions, if I were to go ahead and I were to add sodium hydroxide, in your mind you should be thinking, well, hydroxide is the ion that, this is basically a common ion effect problem. Hydroxide is what's being added, and so that's going to cause the hydroxide ions in my products to increase, which means I'm going to shift to the left. All right? If I shift to the left, that means that the solubility of magnesium hydroxide is going to decrease. This seems like I just repeated myself from the previous section. However, what I'm talking about is pH. So in this case, I increased the pH by adding sodium hydroxide, which then caused a shift to the left, which caused my solubility to decrease. Sodium hydroxide was added, so since that's a common ion, that means that the salt's going to be less soluble. Well, what if I don't add a common ion? What if instead I add hydrochloric acid, for example? Well, that isn't an ion in that dissociation reaction. However, what you should notice is that I'm adding H+. Well, H+ is going to react with hydroxide, which we learned in this unit, and it's going to form water, which means the concentration of hydroxide ions is going to decrease, which means you're going to have a shift to the right. And if you shift to the right, that means your solubility is going to increase. So the second rule here is if you add an ion that's going to remove one of the ions in solution, then the solubility is going to increase. So the only new term here, this is Le Chatelier's principle. The only new concept is this concept of solubility. So if it's shifting to the right, that means that the ionic compound is going to be more soluble. If it shifts to the left, it is less soluble.
So let's actually look at these factors in terms of a problem and look at it mathematically. All right, so I'm told that the KSP for calcium fluoride is 3.9 times 10 to the negative 11th, and it asks me to calculate the solubility, the molar solubility, meaning X, of calcium fluoride in. It's going to give me 3 different solutions. So let's first look at it in water. So I'm going to have calcium fluoride dissociate into calcium ions and fluoride ions. I'm going to create my ice chart. I've got X for calcium fluoride since it's a solid. And since I'm in pure water, my initial concentration of calcium ions and fluoride ions are going to be 0. Then my change is going to be plus X and plus 2X. So my equilibrium concentrations would be X and 2X. So in order to solve for the molar solubility, I need to take I know that KSP equals the concentration of calcium ions times the concentration of fluoride ions squared. So that's going to be X times 2X, that whole thing squared. And that's going to equal my KSP, which is 3.9 times 10 to the negative 11th. So that would become 4X cubed, which equals 3.9 times 10 to the negative 11th. And I solve for that, and I get that X equals 2.1 times 10 to the negative 4th by first dividing by 4 and then raising that to the 1/3, all right, or cube rooting it. So that is my molar solubility in water. Now, based on what we just talked about with the common ion effect, if instead of dissolving it in pure water, if I start off with some calcium nitrate, that means that my molar solubility should be lower than 2.1 times 10 to the negative 4th, according to the common ion effect. So let's see if that's actually the case. It's going to be the exact same setup. My initial concentration of calcium now is going to be 0.10, since I had 0.10 molar of calcium nitrate, so that contributes 0.10 molar of calcium ions. I have a 0 molar solution of fluoride ions. So the rest of this is going to be the same, plus X plus 2X. So my equilibrium concentration would be 0.10 plus X and 2X. Then again, I'm going to plug this into my equilibrium expression, my solubility product. So it's going to be 0.10 plus X times 2X, that whole thing squared. And that's going to equal my KSP. So what I can do is I'm going to use my rule of 100 in order to get rid of the plus X, because otherwise I'm going to have a difficult time solving for X. So since my initial concentration, which is 0.10, divided by my KSP, 3.9 times 10 to the negative 11th, since that's greater than 100, I can get rid of my X, and now I can simply solve it. So I have 4 times 0.1, which is 0.4, times X squared equals my 3.9 times 10 to the negative 11th. Divide both sides by 0.4, and then take the square root, and you get X equals 9.9 times 10 to the negative 6 molar. And that's consistent with your common ion effect, because notice how the solubility is much less than it was when you dissolved it in pure water. Don't believe me? Let's look at another one. Now I'm going to be dissolving it in lithium fluoride. So I have the same dissociation reaction. My initial concentration of calcium ions is 0. Initial concentration of fluoride ions is 0.20 plus X plus 2X, and so you get X and 0.20 plus 2X. Now I need to take the 0.20 plus 2X and square it, and then multiply that by X. Now I'm going to want to use my rule of 100 again. So I note that 0.20 divided by my KSP is greater than 100. Please make sure to show your rule of 100. Don't just get rid of your 2X or your X from the previous problem. Actually show it. So I'm going to get rid of the 2X. Now I have 0.2 squared times X. So that's going to be 0.04X equals my KSP. Divide both sides by 0.04, and I get my molar solubility is 9.75 times 10 to the negative 10th molar. Notice for both B and C, the molar solubility is much smaller than for A, which shows you a mathematical application of the common ion effect.